Hi, let's talk about metallic solids. Go in depth on some metallic bonding. Well, as in depth as you can go for first year general chemistry. Okay, metallic solids. This is when we have a metal and a metal coming together. Now, they don't have to be different metals. You could have pure copper, copper. That's great. That's still going to be metallic bonding. Now, you've already learned that metallic bonding is a sea of electrons. Let's look at that. So it's a solid represented by these positive kernels. That's what we talk about for the atoms themselves. They don't move. It's the electrons that move. So these positive kernels, and then I put in parentheses that this is the core of the nuclei. So it's going to be your nucleus with the protons and the neutrons and the core electrons. Remember, the only electrons that move are the valence electrons in metallic bonding. But it is crazy cool what they do. Those electrons in the valence shell literally delocalize. I wrote it right here. They're mobile electrons. They delocalize, move outside of that valence shell, and then they move and ebb and flow on top of all of those positive kernels, on top of all of the nuclei. I joke that if these could be political, they would be socialists because they all pull together and share. It's the only place where socialism works. Some of you will appreciate that. So I drew this. We've got our positive nuclei with the core electrons, the electrons that aren't in the valence shell. And then you have the mobile electrons, the valence electrons that delocalize, and they move and ebb beautifully on the top of all those positive nuclei. So it's the sea of electrons. When I say sea of electrons, it's this beautiful diagram. Well, not that I drew it beautiful, but it's the beautiful principle of those electrons delocalizing and moving over the core electrons. Now, as a result, every single property on metallic bonding is attributed to this sea of electrons. So metals are very malleable. That means we can bend them, shape them into pots and vases. And they're ductile. We can string them and pull them like taffy. We can extrude those metals. And it's because the nuclei, they don't have to change, and it's the electrons on the outside that allow this bending. So pretty cool. Malleable and ductile because of the sea of electrons. Conducts electricity really well and conducts heat really well. That's why we use metal pans, and this is why we use copper wire. Has a really high melting point and boiling point. Not as high necessarily as ionic. Remember, ionic bonding is stronger than metallic bonding. Just keep that in your mind. Not soluble, won't dissolve in water, and lustrous. The shininess, the beautiful shiny of metals, that is going to be from the sea of electrons. Now, I do want to give a little disclaimer on this high melting point and boiling point. We do have our metals in the group 1 alkali metals right here, and they're actually quite soft. You can cut them with a knife. So there is a range, but for the most part, we say that metallic bonds have high melting points and high boiling points. Now, something that we've exploited, something that we use a lot is alloys. It's where we get a mixture of different metals, put them together, and that's called an alloy. Now, there are two different types of alloys. We have interstitial, and these are going to be atoms that have different atomic radiuses. You're going to have one that's large and one that's small in comparison. And what happens is all of the large atoms line up, and then the small atom fits in, it's called the interstices. It's going to be the little hole in between 4 big atoms. So I drew this for you with an example. Our example is steel. Man, we use steel all the time. So we're going to have carbon and iron. Carbon is the smaller atom, which would make sense. Carbon's in period 2, and iron is in period 4. So iron is going to be our large atom, and then the carbon fits in that little section called the interstices. Notice I have my 4 iron atoms, and carbon sits in the middle. That is an interstitial alloy. Next, substitutional alloys. And I'll tell you just right from the get-go, this is artisan. It really takes a skilled worker to do substitutional alloys. So this is when the atomic radii is comparable, pretty darn close, pretty close in the same size. And really, it just comes up to a random mixture. It's the artisan. How good are they at mixing those metals together? A really good example is brass. This is going to be copper and zinc. So copper, this is my green atom that I drew, and zinc is the purple atom. I notice it's random. It's completely random. It just depends on how well the artisan mixes those metals to make like a brass bell. I had read once, don't know if it's totally true, but our bell in Philadelphia, it's hypothesized that maybe it cracked because the substitutional alloy wasn't mixed well enough. I don't know if it's true or not, but there's a little sidebar that might help you remember brass. Substitutional alloy is really just how good the individual is at mixing those metals together. Now the outflow of alloys, the lattice becomes more rigid because it's a mixture, which means that it's less malleable and less ductile. It's harder. It's going to be harder to form, to move, to bend, and to pull. Now the density of these alloys, the density is simply a weighted average of the elements, the metals inside of that. So let's say that I had 60% copper, 40% zinc. I would take the density of copper, multiply that by 60%, take the density of zinc, multiply that by 60%. Sorry, I can't remember my numbers. Let's say copper was 60%, density times 60%, zinc was 40%, density times 40%. Add those two together, and that's going to be the density of that entire alloy, that new mixture. So we don't do a lot with metallic solids in a first-year chemistry class, but there is a good overview, a good foundation as you go into future classes. If you have questions on molecular solids, on our ionic solids, watch those videos on Lean Think. Thank you. Have a good day.